In this video I will talk about point estimation. Alright, let me return to one of the examples I talked about at the very beginning of this course. Now, you may remember this example. This is an example I talked about where the population consists of all men in the UK, right? And the sample, which we denote by S, contains, suppose say, instead of 100, suppose we say just 3. Say 3 randomly in the UK, and suppose we are interested in estimating the parameter which we denote by theta, which is the average height of all men in the UK, and we need to come up with an estimate for theta. We need to come up with an estimate for theta, which we call theta hat, right? And that is where a question mark comes in. How do we estimate theta, right? Now, in order to estimate theta, we have 3 randomly selected men in the UK, and we have their heights measured. So the data that we have is the following. Suppose x1 is the height of the first man that we selected. Okay. And suppose x2 is the height of the second man we selected, and suppose x3 is the height of the third man. Okay. Now, using these 3 data points, how can we estimate theta? So that's the question mark I have put. Right. So the question is, once again, how can we calculate theta hat? That's the question mark. All right. One way is to add the three heights, right, and divide by 3, and you may call this theta at 1. That's one possible way, right? But that's not the only possible way. We can also estimate, just add the first 2, the heights of the first 2 men, and divide by 2. Alright, and this is not the only possible way. You can add the heights of the first and the third man and divide by 2. And add the heights of the second and the third man and divide by 2 and so on. Right? So there is no one way to estimate the parameter theta. There are multiple ways you can do it. So the question, which one is the best? I mean, you can do it in different ways. Which estimator is the best? So the question we are asking is which which of these is the best estimator for theta? And now, in order to answer this question, I'm going to give you two criteria. So suppose suppose is an estimate, theta hat is an estimator of theta. Now the two criteria, number one is known as the bias. The bias of theta hat is defined as the expectation of theta hat minus theta. The second criteria is known as MFC. It stands for mean squared error. MSC of theta hat, and is defined as the expectation of theta hat minus theta squared. So these are the two criteria. Now an estimator is good if the bias is as small as possible and the MSC is as small as possible. What I mean, so let me write that down. The smaller the bias, the better the estimator. Okay. And the smaller the MSC, the better the estimator. Okay. Right, so a good estimator will have bias as small as possible and MSC as small as possible. Right? Okay. Right. Now suppose you have two estimators, theta 1 hat and theta 2 hat. Right? And the question is which one is better and how you select. Right? So you will select you will select theta 1 hat as the better estimator with respect to bias if the absolute value of theta 1, of the bias of the theta 1 hat, is less than the absolute value of the bias of theta 2 hat. Okay? And you will select as the best estimate with respect to MSC if MSC of theta 1 hat is less than the MSC of theta 2 hat. Okay? Alright, so the better estimate may be different with respect to the two different criteria. So for example, it could be that theta 1 hat is the better estimator with respect to bias, and theta 2 hat is the better estimate with respect to MSC, right? Right, so they need not be the same estimator, right? So it depends on whether you like to minimize the bias or like to minimize the MSC. So if your interest, if the study that you're taking is if the bias is more important for that study, you will choose the estimator that has smaller MSC. For the study you are taking, the MSC is more important than bias, then you will choose the estimator that is smaller with respect to MSC. Right? Okay. Alright, in the next slide I'm going to give you certain definitions. So I'm going to give you 3 definitions. Number 1, an estimated theta hat is unbiased for theta. So the key word here is unbiased if the bias of theta hat is equal to 0. Number 2 is theta hat is asymptotically unbiased for theta if the limit as n approaches infinity of the bias of theta hat is equal to 0. Number 3, an estimated theta hat is consistent for theta if the limit as n approaches infinity of the MSC of theta hat is equal to 0. So these are 3 important definitions you need to know: unbiasedness, asymptotically unbiasedness, and consistency. Alright, in the next slide I will give you 3 properties, and I will also give you proofs of those 3 properties. But before I give the proofs, let me write them down. Let me write down the properties first, then I will prove them. Property 1 says that the MSC of an estimator can be written as the variance of the estimator plus the square of the bias. Right, that's property 1. Property 2, right, it says that an estimator is consistent for theta if and only if these two statements hold. Property 3, if the expectation of theta hat is k times theta, where k is a constant, then theta hat divided by k is unbiased for theta. So these are the 3 properties. Now I will prove each of them, starting with property 1. So there are different ways you can prove this. So I'm going to prove by starting with the left hand side, which is the MSC of theta hat, right? Which by definition is equal to the expectation of theta hat minus theta squared. Okay. Now this you can write as follows. You can write theta hat minus the expectation of theta hat plus the expectation of theta hat minus theta squared. Okay. Now I'm going to put brackets around this. You will see in a minute why I'm doing this. And now you've got something plus something squared, right? So if you open the brackets, you will get 3 terms. And the first term will be this is the first term, right? And the second term will be right, and the third term will be this. Okay. Alright, in the next step I'm going to take the expectation inside the square brackets, right? Okay, so this is, so you will get 3 different expectations. So this is the expectation of this, right, plus 2 times the expectation of plus the expectation of right. Now, if you look at this term here, right, what you have here is precisely the variance of theta hat, right? That's because, all right, let me write it down. You may recall that the variance of a random variable x is defined as the expectation of x minus the expectation of x. This is the formal definition of a variance, right? So using this fact is immediate that this has to be the variance of theta hat, right? So let me put this in a box so that you don't get carried away by this. I don't know. So this becomes equal to the variance of theta hat, right? Plus, now over here, if you look at this here, if you look at this guy here, the expectation of theta hat minus theta is a constant, right? Because the expectation of a random variable is a constant, theta is a constant, so you can pull it outside, right? So you get 2 times right? And once again, but for the same reason, this is also a constant, right? Okay. So the expectation of a constant is itself, right? So what you have is the expectation of square, right? Now, by the way, this is the definition of bias. In a couple of slides ago, I mentioned that the bias of an estimator is defined as the expectation of the estimator minus theta. Right? So this, what you have here is exactly the definition of bias squared. Right? So this is the variance of theta hat plus 2 times. Yeah. Now, I'm going to take the expectation inside the square brackets, so it becomes okay, and plus the square of the bias. Right. Okay, guys, now you should look at this term, the expectation of the expectation, because the expectation of theta hat is a constant. So the second expectation is not needed. So the expectation of a constant is itself. So what you have here is the variance of theta hat plus right. Right, so this is clearly 0. So what you have is the variance of theta hat plus the square of the bias. Right, and this is equal to the right hand side. So hence we have proved property 1. Right. I hope this is clear to you guys. Okay. Right, the next property I'm going to prove is property 2. Okay, to prove this, I'm going to assume theta hat is consistent, which, according to the definition I gave you a couple of slides ago, an estimator is consistent if and only, by the definition, if the limit as n goes to infinity of the MSE of theta hat is 0. Right, so this is the definition I gave you, right? Now, this is the same as saying that the limit that's using by property 1, which I just proved. Okay, MSC is equal to this plus this. Right? Now, because the variance is a non-negative number, but the square of anything is also a non-negative number, the limit of this plus this equal to 0 happens if and only if okay, and okay, and finally, if the limit of the square of the bias is 0, then the limit of the bias has to be 0. So this happens Alright, so this completes the proof of property 2. And in the next slide, I will prove property 3. Okay. So to prove property 3, we must show that the estimator theta hat divided by k is unbiased. So to show that this is unbiased, we need to show that the bias of this is equal to 0. Right? This theta, okay. This is equal to 1 over k. And this is equal to theta minus theta, which is equal to 0. So hence, we have shown that theta hat by k is unbiased for theta, right? Because the bias is 0. Right? So that proves the property property number 3. Alright, so this completes the video on point estimation. In the next video, I will do examples on point estimation. Right? So far, I haven't done any examples, but in the next video, I will do about 10. I hope to do about 10 examples on point estimation.